Hey guys, welcome to the session. So this is Padma Tejaswi and I have done my masters in chemical engineering from NIT Kerala. Yeah. So how are you? Yeah, I think you guys are doing good and well. So how is your preparation? So we are left with any time for a very less time. It's almost like 30 or 25 days, right? So we have a lot to do with what is it? What I mean to say is we have a lot to discuss about heat transfer and mass transfer and CRE. So a lot of subjects to cover, right? So yeah, basically this is a quiz analysis session. So we have covered, this is the second quiz. So I have started a course for heat transfer, part 1, and for GATE chemical engineering students basically. But I have included topics also related to mechanical engineering students. So this course will be useful for both mechanical and chemical engineering students. So yeah, I guess I'm able to clear your doubts. So if you're having any doubts and if you want to know more about heat transfer theory and yeah, numericals, so we have conducted a lot of numerical sessions. So yeah, if you want to practice more and more like difficult models of heat transfer, so do attend the course. And if you haven't taken, so if you don't have a plus subscription, then yeah, do use my code Padma10. So then you'll be getting 10% discount. Okay, so if you use this code, you will be getting 10% discount. So basically, a year-long course for GATE students will be around 25,000. So 10% means 22,500 will be less. So you'll be paying only 22,500 rupees. Okay, so I guess this is a very good offer. So yeah. Uh, Take plus subscription and yeah, attend the courses. Okay, so let's get into the discussion. The main topic that we wanted to discuss is quiz analysis. Okay, so in this quiz I have included topics like few numericals and a few theoretical part. So now yeah, this is related to radiation, right? Because we have all the radiation terms and black body, temperature, right? So by using, like by reading the question at a glance, you should get to know like from which topic it is. Okay. So in this session, I will be discussing you like about the process. So it is your turn and it is your side to answer the question. Okay. So do answer the question and yeah, comment your answers. Okay. So if you are having any doubts and if you are wrong and any calculation mistake, I will correct you. Okay. So yeah, first question. A black body at a higher temperature, Th, transfers energy to a black body at lower temperature, Tc. Okay, so higher temperature is denoted as Th and lower temperature is denoted as Tc. Okay, so first case 1 is this Th is equal to 1850 and Tc is given as 500. See, this is in degrees centigrade. Okay, so whenever you find temperature in degrees centigrade, you have to convert this into Kelvin. Okay, because in radiation, whatever the laws that we are having in, I mean, either it is Stephen Boltzmann law or Planck's law or Wales law, whatever the temperature we are calculating was absolute temperature, means temperature in degrees Kelvin. Okay, so first and foremost thing, what you have to do is to calculate temperature in degrees Kelvin. Okay, so convert this into degrees Kelvin and yeah. So the net amount of energy exchanged is 25 watts. Okay, so when these are the higher and lower temperatures, the energy transferred between the bodies are 25 watts. Okay, after some time, when Th is equal to 1500 degrees centigrade and Tc is equal to 750 degrees centigrade, what is the net rate of energy transfer? Okay, so we are having second case in which Th is equal to 1500 degrees centigrade and Tc is equal to 750 degrees centigrade. Okay, So here we should calculate what is the net rate of energy transfer. This is a very simple and very basic question. Like I guess you will be able to solve this question like within a minute if you are fast in calculations. So put your gate calculator with you and try to solve this question. So I will just tell you what is the basic concept involved here. Okay. So when we have radiation and the black bodies, what is the formula that we use to calculate the net rate of energy transfer? We use Stephen Boltzmann's law, right? Yeah. So what is this law? This law defines that Q is directly proportional to absolute fourth power of the absolute temperatures. But here we are taking net rate of energy transfer, right? So because of this, Q is equal to sigma alpha. So this may be alpha or this may be emissivity. Alpha means absorptivity, right? So either we can use absorptivity or emissivity. So depending upon the heat transfer, right? T1 power 4 minus T2 power 4 or TH power 4 minus TC power 4. So as this is a black body, alpha will be equal to 1, right? So both of them are black bodies, right? So alpha will be equal to 1 and sigma, which is Stephen Boltzmann constant, is same in both the cases, right? So from this, if you compare for first case and second case, Q is only depending upon TH power 4 minus TC power 4, right? So what you can do, Q1 by Q2 is equal to TH power 4 minus TC power 4 in first case by TH power 4 minus TC power 4 in second case. Okay. So for calculating this, the most important thing, TH, temperature of the hot fluid should be in degrees Kelvin. So TH1 is equal to 1850 plus 273. What you will be getting? 3, 2 and 2123, right? So this is 2123 Kelvin, right? And yeah, TC1 is equal to 500 plus 273, which is 773 Kelvin. Okay. So this is for TH1 and TC1. Similarly, TH2 is equal to 1500 plus 273. You will be getting 1773 Kelvin. And TC2. TC2 is equal to 750 plus 273. You'll be getting 3, 2, 8, 9, 10, 1023 Kelvin. Okay. So these are TH1, TC1, TH2, TC2. So we have all the data on right hand side and yeah, Pratyusha. Uh, okay, so Pratyush, I have taken already, I have covered already radiation part. So you can check my course. The name of the course is Complete Course on Heat Transfer Part 1 and Tejaswi Nuli. Okay. So if you go to my profile, you will be seeing the course on heat transfer. So there you can attempt radiation. Okay. That course is already done. Actually, we are in the last session. So yeah. If you want to know more about radiation, then you can go to that class. And if you have any doubts, a doubt clearing session is also there. So then you can clear your doubts. Okay. Okay, Pratyush? Yeah. Okay, mechanical engineering students will also have the same, right? So for you, you'll be having the laws, Stephen Boltzmann law and view factors. Yeah, you can. You can. I have included topics for mechanical engineering students also. So yes, you can attempt that session. Okay. Yeah. So we already have Q1 value. So from this, if you substitute all the values in Q1 and TH1, TC1, TH2 and TC2, you will be able to calculate Q2. Okay. So do the calculations and yeah, the basically answer will be somewhere around 11.01. Okay. So option 1 is the correct answer. Right? Any doubts? Okay, okay. So yeah, next question. So in this question, we have ratio of Nusselt number to Biot number is. Okay, so first of all, what is Nusselt number? It is the ratio of conductive resistance of the fluid to the convective resistance of the fluid, right? So basically, Nusselt number is equal to conductive resistance of fluid to the convective resistance of fluid. Okay. So Biot number, the equation for Biot number is also the same, but here what for, I mean, to which in which state we are calculating conductive resistance and in which state we are calculating convective resistance will differ. Okay. So Biot number is the ratio of conductive resistance and convective resistance only, but the difference between Biot number and Nusselt number is Nusselt number is the ratio of conductive resistance of fluid. Means when fluid is maintained as a when fluid is at rest position. So when fluid is at rest position, there will be no movement of molecules, right? Means convection will be zero. So but in conduction, what happens? There will be no appreciable movement of molecules, but still heat transfer will take place to the adjacent molecules, right? So Nusselt number is conductive resistance of fluid to the convective resistance of fluid, and Biot number is equal to conductive resistance of solid to the convective resistance of fluid. Okay. So now tell me what will be the answer? The ratio of Nusselt number to Biot number will be equal to conductive resistance of fluid to solid of solid. Okay. So option A is the correct answer. Okay. So if you like based on the formula Nu is equal to HL by K, and similarly Biot number is also HL by K. So here also it is characteristic length, and Nusselt number also characteristic length. So if you go with the formula, you will be selecting this option, right? But this is a wrong option. So you should. So that is why I always say that uh, you should calculate, or you should follow the logic based on the logic. So first of all, you should know what is Nusselt number and what is Biot number. Okay. So I guess I'm clear. Yeah. Let us proceed to another question. So in this question, what we have, which one of the following statements about baffles in a shell and tube heat exchanger is false? Okay, so let us go through the options. So first option we have baffles acts as a support to the tube bundles. Okay, and the baffles reduces the pressure drop on the shell side. Okay, and third option is alters the shell side flow pattern, and fourth option is helps in increasing the shell side heat transfer coefficient. Okay, so I guess you'll be by this time you will be able to answer the question. So what is the answer? Option B is the correct answer. Okay, so let me justify the solution. So why we are handling the baffles? So let us suppose that these are shell and tube heat exchanger. Okay, so this is the shell, and yeah. So here there are tube bundles. Okay, so basically the baffles are introduced in the heat exchangers on shell side to increase the flow, means to increase the Reynolds number of the flow. So if you are having a very low viscous fluid and if you introduce baffles, then what happens? This shell side fluid will be coming with certain velocity, right? So when they are when they are attending or when they are conquered with the baffle, what happens? The direction of the fluid changes, or because of this obstruction, the velocity of the fluid will be increased, right? So according to the option C, what we have alters the shell side flow pattern. Yeah, because of this obstruction, the direction of the flow may be changed, right? So maybe they will go in this side, or maybe they will be go in this side, or maybe the direction will be changed to from counter current to co-current, right? So there is a chance of that. So this case will be happened and acts as a support to the tube bundles. Yes, of course, the baffles are used to support these bundles, tube bundles, okay, and helps in increasing the shell side heat transfer coefficient. So as we are changing the flow from laminar flow to like turbulent flow, so because of this, I mean, as we are introducing an obstruction in the flow of the fluid, the Reynolds number of the flow increases, right? So because of this, what happens? Convective heat transfer coefficient on the fluid which is in shell side increases, right? So basically, this will helps you to increase the shell side heat transfer coefficient. But option B, what they have given, reduces the pressure drop on the shell side. No. So as the velocity is increased, what happens? The pressure drop will be increased. Means more pressure will be, like if you are having continuous number of baffles. Okay, so if you are having more number of baffles, then what happens? Because of this, because of this obstruction over here, it will lose some amount of velocity and some amount of energy. So all this pressure will be converted into velocity, right? It will increase the velocity, but still pressure will be affected. So you should take care of, like when we are designing a heat exchanger, you should take care of this factor also. So based on the optimizable quantity, you should design how many number of baffles are to be used and the distance between that is to be maintained between the baffles. Okay. So option B. So if we are having an option like increases the pressure drop on the shell side, then that option will be I mean the statement will be correct. Okay. So yeah, I guess I'm clear. So if you have any doubts, please post your comment. Okay. So next question. Yeah, in this question we have consider two black bodies with surface S1 and yeah. So we are having a surface S1 and the area is equal to 1 meter square. Okay, so we are having another surface S2 whose area is equal to 4 meter square. Okay, so they say that the exchange heat only by radiation. Only the heat transfer is taking place through radiation. Okay, and 40% of the energy emitted by S1 is received by S2. So what does this mean? The energy emitted by S1 is received by S2. What does that mean? What is this trying to say about? They are trying to say about view factors. So F12 is equal to zero point 0.4 means the fraction of energy emitted by. So what is view factor? This F12, the energy fraction of energy emitted by surface 1 and received by surface 2, right? So this will be equal to 0.4 and they are asking about fraction of energy emitted by S2 that is received by S1. So they were asking about what is F21. So in radiation, the basic and simple properties that we should remember is F12 plus F11 is equal to 1 and F12A1 is equal to F21A2. Okay. So when you're having like heat exchange between two bodies through radiation, the basic properties that we should know is this. Means the summation of fraction of energies which is emitted by a surface, I mean from a particular surface, but it is received by numerous surfaces is equal to 1. Okay. So yeah. So in this question, what is the property that will be useful to us? It is this. Because F12A1 is equal to F21A2, right? So by using this, F12A1 is equal to F21A2. So we have F12 as 0.4 into A1 as 1, which is equal to F21 into 4, right? So F21 is equal to 0.4 by 4, which is nothing but 0.1. So the fraction of energy emitted by S2 and yeah, received by S1 is 0.1. Okay. So is that clear? Yeah, I guess you are clear with this. So let us proceed to next question. Yeah, this is a very simple question. This can be solved in like 15 seconds. So for an ideal black body, what is the properties? So obviously for an ideal body, whatever the radiations that are absorbed is equal to, I mean, a black body is one which absorbs all kinds of radiations, right? So because of this, absorptivity is equal to 1, and we have the property as absorptivity plus transmittivity plus, sorry, this absorptivity plus transmittivity plus reflectivity is equal to 1. So as this is 1, reflectivity is equal to gamma is equal to 0. So there will be no radiations which are reflected, or there will be no radiations which are getting transmitted in a black body. But we are having another option which is emissivity is equal to 0. So can we say that emissivity is equal to 0 for a black body? No, because, so what is emissivity? The radiations which are emitted from a body, right? So if a body is having a temperature greater than absolute zero, means if the temperature of the body is greater than minus 273 degrees centigrade or greater than 0 Kelvin, then obviously some amount of energy will be stored. Okay, so there will be some amount of energy stored in a particular body. If you consider any body, like whether it is gas or whether it is fluid, any kind of body, if the temperature is greater than 0 Kelvin, then it will have some amount of energy, and this energy will be emitted. Okay, so if we are having a black body and if we are observing some radiations which are emitted, then it is the that internal energy stored within self inside the body. Okay, so because of this, emissivity is not equal to 0. Okay, so we can't say that these rays are reflected rays or transmitted waves. Okay, because it is not about reflectivity or transmittivity, it is about emissivity. Okay, so I guess you know the difference between reflectivity, transmittivity and emissivity. Okay, so yeah, so option A is the correct answer. Okay, so if you don't if you have any doubts regarding radiation, and if you have any doubts regarding view factor calculations, okay, so how based on insulation, when a material is insulated, how F11 value changes, and yeah, when you are having both a black body and a real body, how this value will be affected. So you can attend the course, and you can attend my course heat transfer part 1, and from that you will be able to uh, clear your doubts. Okay, but still if you are if you still attend the question, and if you still have any doubts regarding radiation, so please comment your questions over here, and I will be taking a separate session regarding this, and I will clear your doubts. Okay, so now steam economy of a multiple effect evaporator is defined as. So what do you mean by economy? Economy means the amount of steam generated, or the amount of vapor that is generated per kg of steam that is fed. Okay, means let us suppose that we are heating the process, I mean the evaporator, with 1 kg of steam. Okay, and the concentration is, initial concentration is 2% and final concentration is 30%. Okay, means the product concentration is 30%. So means the remaining fluid, whatever in the liquid state, is vaporized, right? So we are generating this particular x kg of vapor, right? So according to the definition of economy, the amount of vapor generated per kg of steam will be x by 1. Okay, so okay, so this is the correct option. Okay, so what will be the correct option? So let us go through the options. first option is kilogram of steam used per hour. No, this is determining about the capacity. Means how much amount of steam is water vapor or steam at low pressure coming out per unit time. Okay. Okay, this is also not about capacity. If we have vapor produced per, okay, so capacity will be kg of vapor produced per unit time. Okay, so there is nothing to do with the steam that is used. Okay, yeah, so this is capacity and this is economy. So first option is wrong and second option. Kg of steam consumed in all the efforts for each kilogram of steam fed. So this is also not the correct option because here they were telling about kg of steam consumed. Okay, so this is not the correct option. And the third option, kg of steam used in all the efforts of for each kilogram of water vaporized per hour. So this is basically the inverse of uh, economy. Okay, so option D is the correct answer, which means kilogram of vapor, water vaporized from all the efforts for each kilogram of steam fed to the first effect, which means the amount of water vaporized by the amount of steam fed in the evaporators, right? So this is about economy. Okay, so I guess I'm clear with the question. So yeah, let us proceed to the next question. So here what we have, calculate the heat required to rise the temperature of 1 mole of the solid material from 100 degrees centigrade to 1000 degrees centigrade. So N is equal to 1 and T1 is equal to 100 and T2 is equal to 1000, right? And specific heat of the material C is given as 20 plus 0.005 T. So assume that there is no phase change. So when there is no phase change, it is only sensible heat, right? So sensible heat can be given as dq is equal to ncp dt, right? So when you integrate this equation, you will be getting q because this is a path function, right? So the integration of a finite, a very small value of a path function will be giving you a finite value. Okay, so n is equal to 1, so integral t1 to t2, and cp is a function of temperature, right? So because of this, 20 plus 0.005 t dt. So what you'll be getting q value as, q is equal to 20t plus 0.005 t square by 2. The terms of, the lower limits and upper limits are 100 degrees centigrade and 1000 degrees centigrade. So don't forget to convert this degree centigrade to Kelvin. Okay. So the upper limits will be 370. The lower limit will be 373 and upper limit will be 1273 Kelvin. Okay. So don't forget to substitute this. And see here, why I'm telling this to substitute in degrees Kelvin, because they have mentioned that where T is in Kelvin. So if you miss this quantity, then whatever you are calculating, it will be wrong. Okay, so be careful with the calculations and dimensions that you are using with temperature. Okay, so yeah, if you substitute, you will be getting an answer. So please comment your answer. Yeah. Now next one. So this is a like theoretical question. So Prandtl number for dry gases is of the order 1. Okay. So this is not a very important question, but if you have information about this, there is nothing wrong in that, right? So yeah, next question. Heat flux as defined in heat flow is analogous to dash and current flow. Okay. So in electricity flow, what is the thing that we are that is transferring? It is current, right? So in heat flow, will be discussing about the heat flux, and in electricity flow, we'll be discussing about current. Okay. So current is the correct option. Next question. And if you are having mass flux, then it will be analogous I mean, in mass transfer it will be mass flux is the term which is analogous to the heat flux. Okay, yeah. Which of the following has the maximum thermal conductivity at the same temperature? So according to the properties of thermal conductivity, conductivity of solids is greater than liquids is greater than gases, right? So here, this is a solid and this is a liquid and this is a gas. So obviously, conductivity of steel will be greater than conductivity of petrol, which is greater than conductivity of air, right? So you should know that properties of conductivity is also no, voltage will be heat transfer. No, I didn't answer your question. Okay, you are saying that voltage is the will be heat transferred. No, see, like in electricity flow, what is the measurement that we will be, yeah, that we will be discussing about current, right? What is the measured? We will, with the help of this voltage, like E is equal to, yeah, okay, so uh, let me just remember the formula. Um, See, I don't remember the formula. So see, in electricity flow, what is this that we, yeah, V is equal to IR. Okay, not this. See, in heat flow, what happens with the help of temperature? We are calculating heat flux, right? So Q by A is equal to delta T by delta X, right? At the same time, in electricity flow, with the help of voltage, we will be calculating the measure of current. Okay? Yeah, voltage is equal to current into resistance. I agree with that. So here, what is heat flow? Heat flow is equal to potential difference by resistance. I mean, flux is equal to potential by resistance. Right? Is this correct? So now current will be equal to voltage by resistance, right? So if in heat transfer, if they ask like what is analogous to temperature difference, then you can say that it is analogous to voltage. Okay, so is that clear now? So from this property, flow is equal to potential by resistance, and here what is the flow? It is heat flow, right? Which is nothing but heat flux. Yeah. So current is equal to voltage by resistance. Okay. So don't get confused. Uh, like write the terms particularly. Okay. So whatever you have mentioned, it is current into resistance. So if they ask about potential flow, then it is temperature will be analogous with the voltage. Okay. So yeah. Um, okay. I guess I'm clear now. So yeah, if you haven't taken class subscription, use my code Padma10. Then you'll be getting 10% discount. And if you like the session, share it with your friends. So yeah, share it with your friends and like the session. Okay. So yeah, this is me signing off. So Pratyush, do log into the session, which is under Tejaswi Nuli. So you will be able to edit the course, okay, based on radiation. Yeah. Have a good day and yeah, enjoy your holiday.